Alright, hello everyone, welcome back. I'm your friend XO. Today this is the last lesson for the high school geometry, and we're gonna end it here. So the last version we're gonna learn is called solid geometry. What is solid? 2D with 3D objects, dilating in 3D.
Let's say I have some type of a surface. Let's say that this right over here is the top of your desk, and I were to draw a triangle on that surface. So maybe the triangle looks like this, something like this. It doesn't have to be a right triangle, and so I'm not implying that this is necessarily a right triangle, although it looks a little bit like one. And let's call it triangle A, B, and then C. Now what I'm going to do is something interesting. I'm going to take a fourth point P that's not on the surface of this desk, and it's going to be right above point B. So let me just take that point, go straight up, and I'm going to get to point P right over here. Now what I can do is construct a pyramid using point P as the peak of that pyramid. Now what we're going to start thinking about is what happens if I take cross sections of this pyramid. So in this case, the length of segment PB is the height of this pyramid. Now if we were to go halfway along that height, and if we were to take a cross section of this pyramid that is parallel to the surface of our original desk, what would that look like? Well, it would look something like this. Now you might be noticing something really interesting. If you were to translate that blue triangle straight down onto the surface of the table, it would look like this. And when you see it that way, it looks like it is a dilation of our original triangle centered at point B. And in fact, it is a dilation centered at point B with a scale factor of 0.5. And you can see it right over here. This length right over here, what BC was dilated down to, is half the length of the original BC. This is half the length of the original AB. And then this is half the length of the original AC. But you could do it at other heights along this pyramid. What if we were to go 0.75 of the way between P and B? So if we were to go right over here. So it's closer to our original triangle, closer to our surface. So then the cross section would look like this. Now if we were to translate that down onto our original surface, what would that look like? Well, it would look like this. It would look like a dilation of our original triangle centered at point B, but this time with a scale factor of 0.75. And then what if you were to go only a quarter of the way between point P and point B? Well, then you would see something like this. A quarter of the way, you would take the cross section parallel to our original surface. It would look like this. If you were to translate that straight down onto our table, it would look something like this. And it looks like a dilation centered at point B with a scale factor of 0.25. And the reason why all of these dilations look like dilations centered at point B is because point P is directly above point B. But this is a way to conceptualize dilations or see the relationship between cross sections of a three-dimensional shape, in this case like a pyramid, and how those cross sections relate to the base of the pyramid. Now let me ask you an interesting question. What if I were to try to take a cross section right at point P? Well, then I would just get a point. I would not get an actual triangle, but you could view that as a dilation with a scale factor of 0. And what if I were to take a cross section at the base? Well, then that would be my original triangle, triangle ABC, and then you could view that as a dilation with a scale factor of 1, because you've gone all the way down to the base. So hopefully this connects some dots for you between cross sections of a three-dimensional shape that is parallel to the base and notions of dilation.
Alright, this video just tells us a simple fact, which is dilation in 3D model is just related to the base 2D shape. They share the same scale value or scale factor. Slicing a rectangular pyramid. What is that?
So I have a three-dimensional solid right over here, and I want to imagine what type of a shape I would get if I were to make a vertical cut. And just to refresh ourselves or give us a sense of what a vertical cut is, imagine if this was made out of jello or something kind of fairly soft, but it's still a three-dimensional solid, and I were to make a cut. Let's say I were to make a cut right over here. So let's say I have this big sharp metal thing. Let me draw it like that. So you have this big sharp metal thing. Let me draw it a little bit neater. So you have this big sharp metal thing that I'm going to cut right over here. So this is the thing that I'm going to make the cut, and I'm going to go straight down. This is a vertical cut that we're talking about. This is the thing that I'm going to cut with. All right, let me make it big enough so that it can capture the shape that will result. So this thing right over here, it's right in front, and I'm going to make it go straight down and cut through this jello, or whatever you want to call it, this rectangular pyramid of jello. And what would be the resulting shape of the intersection between that jello and this thing that I'm using to cut it? And now I encourage you to pause your video and think about what the resulting shape would be. And the shape would be in 2 dimensions, because this purple surface is a 2-dimensional, it's a 2-dimensional, you could view it as a part of a plane. And so where this intersects when you cut down this rectangular pyramid is the shape we're looking for. So I encourage you to pause the video and think about it, or try to come up with it on your own. So let's think about it, and let me draw the rectangular pyramid again. So that's the same one. And now let me see what it would look like once I've done my cut, once I've brought this thing down. So then this is where I cut. So I cut it right over here, and then it'll exit the bottom. It'll cut along this side like that, cut along that side like that, and then it'll exit the bottom. Right over there. And let me draw my whole thing. And so once I slice it down, it will look like this. My best shot at drawing it. It will look like this. This is a vertical cut. So I brought this thing down, and now the intersection between the thing that I'm cutting with and this pyramid is going to be this shape right over here. It cut into the top right over there. It would get all the way to the bottom right over there, and along this side, it would cut right there, and along that side, it would cut right over there. So what's the resulting shape in 2 dimensions of essentially the intersection between the slicer and the jello? Well, it would be this thing. It would look like a trapezoid. Let me do that in a new color. I'm overusing that one color. It would look like a trapezoid. So this would be the resulting shape. So the resulting shape would look like this. Just like that, if you made the cut right over there.
Yeah, what's the point for doing this video?
It would cut.
Oh, maybe it's just he wanna show you the fact that if you use a plane to cut what's that shape again? Pyramid? I don't know. If you do that cut, you get a shape like this. Ways to cross-section a cube.
What I want to do in this video is explore the types of 2-dimensional shapes we can construct by taking planar slices of cubes. So what am I talking about? Well, let's say we wanted to construct a square. How could we slice a cube with a plane to get the intersection of this cube and that plane to be a square? Well, imagine if that plane were to cut just like this. A square is maybe the most obvious one. So it cuts the top right over there, cuts this side right over here, cuts this side right over here. It cuts this side, I guess in the back, if it's a glass cube, you'd be able to see it right over there, dotted line, and then it cuts this right over here. So you could imagine a plane that did this. And if I wanted to draw the broader plane, I could draw it like this. Let me see if I can do an adequate job of drawing the actual, I guess you could say, part of the plane that is cutting this cube. It could look something like this. And I could even color in the part of the plane that you could actually see if the cube were opaque, if you couldn't see through it. But if you could see it through it, you would see this dotted line, and the plane would look like that. So a square is a pretty straightforward thing to get if you're doing a planar slice of a cube. But what about a rectangle? How can you get that? And at any point, I encourage you, pause the video and try to think about it on your own. How can you get these shapes that I'm talking about? Well, a rectangle you can actually cut like this. So if you cut this side like this, and then cut that side like that, and then you cut this side like that. I think you see where this is going. This side like that, and then you cut the bottom right over there. Then the intersection of the plane that you're cutting with. So the intersection, let's see, this could be the plane that I'm actually cutting with. So the intersection of the plane that I'm cutting with and my cube is going to be a rectangle. So it might look like this. And once again, let me shade in the stuff. If you kind of view this, if you imagine the plane is like one of those huge blades that magicians use to saw people in half, or pretend like or give us the illusion of sawing people in half, it might look something like this. Okay, so you're like, okay, I that's not so hard to digest, that I can, if I intersect a plane with a cube, I can get a square, I could get a rectangle. But what about triangles? Well, once again, and pause the video if you think you can figure it out. Triangle's not so bad. You could cut this side right over here, this side right over here, and this side right over here. And then and of course I could keep drawing the plane, but I think you get the idea. This would be a triangle, and there's different types of triangles that you can construct. You could construct an equilateral triangle. So as long as this cut is the same length as this cut right over here, is the same length as the length that it intersects on this face of the cube, that's going to be an equilateral triangle. If you pushed this point out more, actually let me do that in a different color. If you pushed it out more, you're going to have an isosceles isosceles triangle. You're going to have an isosceles triangle. If you were to bring this point really, really, really close, like here, you would approach having a right angle, but it wouldn't be quite a right angle. You'd still have, these angles would still be less than 90 degrees. You can approach 90 degrees. So you can't quite have an exactly a right angle. And so you can't get to 90 degrees. You're definitely not going to get to 91 degrees. So you're actually not going to be able to do an obtuse triangle either. But you can do an equilateral, you can do an isosceles, you can do scalene triangles. I guess you could say you could do the different types of acute triangles. But now let's do some really interesting things. Can you get a pentagon by slicing a cube with a plane? And I really want you to pause the video and think about it here, because that's just a fun thing to think about. How can you get a pentagon by slicing a cube with a plane? All right, so here I go. This is how you can get a pentagon by slicing a cube with a plane. Imagine slicing the top. Let me do it a little bit different. So imagine slicing the top right over there. So we imagine slicing the top like this. Then imagine slicing this backside. Imagine slicing this backside like that. This backside that you can't see quite like that. Now you slice this side right over here like this, and then you slice this side right over here like this. This could be, and if I wanted to draw, well, the plane, it maybe won't be so obvious if I try to draw the plane, but you get the actual idea. If I slice this, the right angle, not at a right angle, at a right angle. Actually, I shouldn't.
All right. So this is all this video about. He just tried to give you some ideas about, how it could be if we put a plane into a cube. What kind of 2D shape that we could get from it.
Cavalieris principle and dissection methods.
Come on, what is that?
So we have two cylinders here, and let's say we know that they have the exact same volume. And that makes sense because it looks like they have the same area of their base and they have the same height. Now what I'm going to do is start cutting up this left cylinder here and shifting things around. So if I just cut it in two and take that bottom cylinder, that bottom half, and shift it a bit, have I changed its volume? Well, clearly I have not changed its volume. I still have the same volume. The combined volume of both of these half cylinders, I could say, are equal to the original cylinder. Now, what if I were to cut it up even more? So let me cut it up now into 3. Well, once again, I still haven't changed my original volume. It's still the same volume as the original. Now I just cut it up in 2/3. And if I shift them around a little bit, I'm not changing the volume. And I could keep doing that. I could cut it up into a bunch of them. Notice, this still has the same original volume. I've just cut it up into a bunch of sections, I've cut it horizontally, and now I'm just shifting things around, but that doesn't change the volume. And I can do it a bunch of times. This looks like some type of poker chips or gambling chips, where I could have my original cylinder, and now I've cut it horizontally into a bunch of these, I guess you could say chips, but clearly it has the same combined volume. I can shift it around a bit, but it has the same volume. And this leads us to an interesting question, and it's actually a principle known as Cavalieris principle, which is if I have two figures that have the same height, and at any point along that height, the cross-sectional area is the same, then the two figures have the same volume. Now, how does what I just say apply to what's going on here? Well, clearly both of these figures have the same height, and then at any point here, wherever I did the cuts, at this point, at the same point on this original cylinder, well, my cross-sectional area is going to be the same, because it's going to be the same area as the base in the case of this cylinder, and so it meets Cavalieris principle. But Cavalieris principle is nothing exotic. It comes straight out of common sense. I can just do more cuts like this, and you can see that I have, you could say, a more continuous looking skewed cylinder, but this will have the same volume as our original cylinder. When I shift it around like this, it's not changing the volume. And that's not just true for cylinders. I could do the exact same argument with some form of a prism. Once again, they have the same volume. I could cut the left one in half and shift it around, doesn't change its volume. I could cut it more and shift those around, still doesn't change the volume. So Cavalieris principle seems to make a lot of intuitive sense here. If I have two figures that have the same height, and at any point along that height, the cross-sectional area is the same, then the figures have the same volume. So these figures also have the same volume. And I could do it with interesting things like, say, a pyramid. These two pyramids have the same volume, and if I were to cut the left pyramid halfway along its height and shift the bottom like this, that doesn't change its volume. And I can keep doing that with more and more cuts. And because at any point here, these figures have the same height, and at any point on that height, the cross-sectional area is the same, and so they have the same same volumes. But once again, it is intuitive. And it goes all the way to the case where you could view it as a continuous pyramid right over here that has been skewed. So no matter how much you skew it, it's going to have the same volume as our original pyramid because they have the same height, and the cross-sectional area at any point in the height is going to be the same. We can actually do this with any figure. So these spheres have the same volume. I could cut the left one in half, halfway along its height, and shift it like this. Clearly, I'm not changing the volume, and I could make more cuts like that, and clearly it has still the same volume. And this meets Cavalieris' principle because they have the same height, and the cross section at any point along that height is going to be the same. So even though I can cut that one up and I can shift it, it looks like a different type of object, a different type of thing, but they have the same height, and the cross sections at any point are the same area. So we have the same volume, which is a useful thing to know, not just to know the principle, but hopefully this video helps you gain some of the intuition for why it makes intuitive sense.
Okay, the Cavalieris principle in 3D is just talking about if you get two figure, maybe not two figure, if you get two 3D models, and if they have the, let's say, the same length, and then if they have this if they have the same height, and for each part if they have the same weight, then the two figures are equal. I mean, in value they are equal.
So I have two different three-dimensional figures here. I have a pyramid here on the left, and I have a cone here on the right. And we know a few things about these two figures. First of all, they have the exact same height. So this length right over here is h, and this length right over here, going from the peak to the center of the base here, is h as well. We also know that the area of the bases is the same. So for example, in this left pyramid, the area of the base would be x times, and let's just assume that it is a square. So x times x, so the area here is going to be equal to x squared. And the area of the base, so that's area of this base is equal to x squared. And the area of this base right over here would be equal to, area is equal to pi times r squared. And I'm saying that these two things are the same. So we also know that x squared is equal to pi r squared. Now my question to you is, do these two figures have the same volume, or is it different? And if they are different, which one has a larger volume? Pause this video and try to think about that. All right, now let's do this together. Now, given that we're talking about two figures that have the same height, and that at least the area of the base is the same, you might be thinking that Cavalieris' principle might be useful. And just a reminder of what that is, Cavalieris' principle tells us that if you have two figures, and we're thinking in three-dimensional version of Cavalieris' principle, if you have two figures that have the same height, and at any point along that height, the cross-sectional area is the same, then the figures have the same volume. So what we need to do is figure out, is it true that at any point in this height, do these figures have the same cross-sectional area? Well, to think about that, let's pick an arbitrary point along this height. And just for simplicity, let's pick halfway along the height, although we could do this analysis at any point along the height. So halfway along the height there, halfway along the height there. So this distance right over here, that would be h over 2. This distance right over here would be h over 2. This whole thing is h. And what we can do is construct what look like similar triangles, and we can even prove it to ourselves that these are similar triangles. So let me construct them right over here. And the reason why we know they're similar is that this line is going to be parallel to this line, and that this line is parallel to that line, to that radius. And how do we know that? Well, we're taking cross-sectional areas that are parallel to the base, that are parallel to the surface on which it sits in this situation. So in either case, these cross sections are going to be parallel. So these lines which sit in these cross sections, or sit on the base and sit in the cross section, have to be parallel as well. Well, because these are parallel lines, this angle is congruent to that angle. This angle is congruent to this angle, because these are transversals across parallel lines, and these are just corresponding angles. And of course, they share this angle in common. And here you see very clearly right angle, right angle. This angle is congruent to that angle, and then both triangles share that. And so the smaller triangle, in either case, is similar to the larger triangle. And what that helps us realize is that the ratio between corresponding sides is going to be the same. So if this side is h over 2 and the entire height is h, so this is half of the entire height, that tells us that this side is going to be half of r. So this right over here is going to be r over 2. And this side over here, by the same argument, is going to be x over 2. And so what's the cross-sectional area here? Well, it's going to be x over 2 squared. So it's going to be x over 2 squared, which is equal to x squared over 4, which is 1/4 of the base's area, which is equal to 1/4 of the base's area. And what about over here? Well, this cross-sectional area is going to be pi times r over 2 squared, which is the same thing as pi r squared over 4, or we could say that is 1/4 pi r squared, which is the same thing as 1/4 of the area of the base. The area of the base is pi r squared. Now we're saying 1/4 pi r squared. So this is going to be equal to 1/4 the area. And we already said that these areas are the same, and so we've just seen that the cross-sectional area at that point of the height of both of these figures is the same. And you could do that 1/4 along the height, 3/4 along the height. You're going to get the same exact analysis. You're going to have two similar triangles, and you're going to see that you have the same areas, same cross-sectional areas at that point of the height. And so therefore, we see by Cavalieris' principle in 3 dimensions that these two figures have the same volume. And what's interesting about that is it allows us to take the formula, which we've proven and gotten the intuition for in other videos, for the volume of a pyramid. We've learned that the volume of a pyramid is equal to 1/3 times base times height, and say, well, this one must have the exact same volume. It must also be volume is equal to 1/3 times the area of the base times the height. Because in both of these cases, the area of the base is the same and the height is the same, and we know that they have the same volume.
Maybe despite of that basic inclusion, we also probably have another one, which is if you cut this kind of stuff at the center of this pyramid, you get a new area, right? And the new area will be 2 squared times, let's say, the base area is 2 squared numbers bigger than the center area that we just cut. It is different than the length. The length would be just 2 times smaller than the base area, but the area it's 2 squared times smaller. Volume and the surface area. All right, let's get into the first video.
Let's do some solid geometry volume problems. So they tell us shown as a triangular prism. And so there's a couple of types of 3-dimensional figures that deal with triangles. This is what a triangular prism looks like, where it has a triangle on 2 faces, and they're kind of separated. They're kind of have rectangles in between. The other types of triangular 3-dimensional figures is you might see pyramids. This would be a rectangular pyramid because it has a rectangular, or it has a square base, just like that. You could also have a triangular pyramid where it's just literally every side is a triangle, so stuff like that. But this over here is a triangular prism. I don't want to get too much into the shape classification. If the base of the triangle B is equal to 7, the height of the triangle H is equal to 3, and the length of the prism L is equal to 4, what is the total volume of the prism? So they're saying that the base is equal to 7. So this base, this right over here is equal to, base is equal to 7. The height of the triangle is equal to 3. So this right over here, this distance right over here, H is equal to 3. And the length of the prism is equal to 4. So I'm assuming it's this dimension over here is equal to 4. So length is equal to 4. So in this situation, what you really just have to do is figure out the area of this triangle right over here. We could figure out the area of this triangle, and then multiply it by how much you go deep. So multiply it by this length. So the volume is going to be the area of this triangle. Let me do it in pink. The area of this triangle. We know that the area of a triangle is 1/2 times the base times the height. So the area, this area right over here, is going to be 1/2 times the base times the height. And then we're going to multiply it by like kind of our depth of this triangular prism. So we have a depth of 4. So then we're going to multiply that times the 4, times this depth, times the 4. And we get, let's see, 1/2 times 4 is 2. So these guys cancel out. You'll just have a 2. And then 2 times 3 is 6. 6 times 7 is 42. And it would be in some type of cubic unit. So if these were in, I don't know, centimeters, it would be centimeters cubed. But they're not making us focus on the units in this problem. Let's do another one. Shown is a cube. If each side of the cube, or if each side is of equal length, x equals 3, what is the total volume of the cube? So each side is equal length x, which happens to equal to 3. So this side is 3. This side over here, x is equal to 3. Every side, x is equal to 3. So it's actually the same exercise as the triangular prism. It's actually a little bit easier when you're dealing with the cube, where you really just want to find the area of this surface right over here. Now this is pretty straightforward. This is just a square, or it would be the base times the height. Or since they're the same, it's just 3 times 3. So the volume is going to be the area of this surface, 3 times 3, times the depth, times the depth. And so we go 3 deep. So times 3. And so we get 3 times 3 times 3, which is 27. Or you might recognize this from exponents. This is the same thing as 3 to the third power. And that's why sometimes if you have something to the third power, they'll say you cubed it. Because literally, to find the volume of a cube, you take the length of one side and you multiply that number by itself 3 times, one for each dimension. One for the length, the width, and or I guess the height, the length, and the depth, depending on how you want to define them. So it's literally just 3 times 3 times 3.
Okay, this video just reminds me some theory. Let's say, okay, call it. So basically, in that theory, they said that you can use, let's say, infinite or multiple different kind of waves. If you sum them together, you can construct any function that you want. It's kind of like the value calculation. You just have to take one piece of that object, then you combine those pieces together, then you get the value. It's just something like this one. Okay, they call this theory
Fourier transform.
Fourier transfer. All right. Okay, basically all these sections are talking about how can you get the value of a specific 3D object. For example, the coin. For the first one, it's a cube. Then it's a sphere. Sphere is actually the 3D model for a circle. If you rotate your circle 360 degrees, you'll get a sphere. If you don't know what I mean, let me just do a search for you. Alright, it's just something like this. And here we go, you got the formula to calculate the value of a sphere. So basically you don't have to watch them all you have to do is to do some search to get those formula to be able to do that kind of calculation. And then here comes a new concept called density.
In this video, we're going to talk about density in the context of area. And the simplest way of thinking about it is density is going to be some quantity per unit area. So for example, let's say that I have a football field right over here, and I have another identical football field right over here. Now they have the same area, but if I have, let's say, 5 people on this football field, actually 6 people on this football field, and I only have 3 people on this football field, the density of people per average unit area, or the density of people, I should say, per football field, is going to be higher in this left example. So it's always going to be quantity per area. Now with that out of the way, let's do a worked example that helps us understand this idea a little bit better. So here we're told the town of Tigersville has a population density of 13 cats per square kilometer. So they're giving us the density. Let me write that. 13 cats, so the quantity is quantity in cats per square kilometer. That's the density right over there. The town is shaped like a perfect isosceles trapezoid. So it looks something like this. It's a perfect isosceles trapezoid. So it's going to look something like that, with 2 parallel boundaries 12 kilometers apart. So this distance right over here is 12 kilometers. One measuring 8 kilometers, so this side over here is 8 kilometers, the other is 16, that's the longer one over there. How many cats are in Tigersville? So they give us the density here, and they give us, I think, enough information to figure out the area, and they want us to figure out how many cats we have. So what is the quantity? So pause this video and see if you can figure that out. Well, just as we said that density is equal to quantity divided by area, if we multiply both sides of this equation by area, you get area times density is going to be equal to quantity. And we know the density, it's 13 cats per square kilometer, and we can figure out the area and then just multiply the two. So what's the area of this right over here? Well, the area of a trapezoid is going to be, let me write it here, area is going to be 12 kilometers, the height of the trapezoid, times the average of the two parallel sides, I guess you could say. So the average of those, so it's going to be 8 kilometers plus 16 kilometers over 2. So this is going to be equal to 12 kilometers times 8 plus 16 is 24, divided by 2 is 12. So times 12 kilometers. So this gives us 144 square kilometers. Now we know we have 13 cats per square kilometer. So let me do this here in another color. So if I multiply 13 cats per kilometer squared, and I multiply that times this business right over here, times 144 square kilometers. And you might also notice that the units cancel out the same way that variables might. So that cancels out with that. You're going to get 13 times 144, and then the units that you're left with is just cats. So 144 times 13. 3 times 4 is 12. 3 times 4 is 12. That gives us to 13. 3 times 100. 300 plus another 100 is 400. Now I'm just going to multiply 144 essentially by 10, which is just going to be 1440. And so if I add up all of that together, I'm going to jump down to here, I get 1872. So this is 1872 cats in total. And we are done.
Okay, so what he just did is if they know, or if we know how many staffs in a certain unit of area is a normal ratio or common ratio, then we could apply that quantity to a large field, and all we have to do is to do some multiplication, and that's it. And we could get the possibility, we could get the possible that kind of stuff in a large field. I hope you understand what I was talking about. Alright, so this is today's math video, and basically we just have finished the high school geometry lessons after so many videos. Finally, we were done. So we in the next video we could be able to go to a higher level of mathematics learning. Yeah, that's cool. I hope you enjoy this video, and I will see you guys in the next one. Bye.